In medical imaging, image segmentation is useful for the detection of anomalies and the extraction of biomarkers. Recently, deep learning showed its potential when handling image segmentation tasks, especially with supervised learning. It's able to learn complex tasks and process a huge amount of data efficiently compared to classic methods. However, in order to achieve task generalization and human-like performance, deep learning-based methods require a large and diversified training set that reflect real-world data diversity. Since the obtention of such labeled dataset may be tedious, costly, and time-consuming, the attention of the medical image community drifted towards semi-supervised learning methods, which can exploit unlabeled data in addition to the scarcely available labeled data. When discussing semi-supervised learning methods for image segmentation, we can group them into three categories. First, consistency and regularization methods. They usually constrain the model to give consistent prediction for the same unlabeled data under different perturbations. Second, pseudo-labeling strategies automatically assign labels to unlabeled data in order to use them during training in combination with labeled data. Third, auxiliary tasks are secondary objectives combined with the main segmentation task to implicitly learn the extraction of relevant features. However, these methods have some limitations. First, consistency regularization methods originally designed for classification are not adapted for segmentation. Second, pseudo-labeling is prone to error propagation, also known as confirmation bias. Third, the choice of the auxiliary task highly depends on the addressed problem, which limits the method generalization for other segmentation tasks. The proposed method is progressive pseudo-labeling with consistency regularization and neighboring, we will refer to as popcorn. It's designed for semi-supervised learning in segmentation. Popcorn combines consistency regularization and pseudo-labeling in a way that complement each other. On one hand, we base our consistency regularization on the constraint that images with similar segmentation masks should produce similar features. We apply this criteria at the bottleneck of the segmentation network by reducing feature map distance for these particular images. On the other hand, we perform progressive pseudo-labeling with the intent of selecting at each step a group of unlabeled data that we consider similar to the current training set. The similarity is estimated by computing the distance between image latent representation that we extract from the network bottleneck. In the first step, the segmentation network is trained with labeled data only. In the second step, the trained segmentation network is used to compute for each available unlabeled data both a segmentation mask and the latent representation from the bottleneck in order to construct a proximity graph. Then, the selected data points are added to the training set with pseudo-labels computed from the predicted segmentation masks. In the third step, we continue the training of the segmentation network with the updated training set. At this point, we repeat step 2 and 3 in cycle, and we add more and more unlabeled data to the training set. The main intuition is that our segmentation model is able to produce more accurate pseudo-labels for images similar to our training set. Since our consistency regularization ensures close features for similar data, features extracted from the model are used to select new samples. In order to experiment our method, we have chosen the task of multiple sclerosis lesion segmentation. Practically speaking, the model should receive a FLAIR MRI as input and predict the MS lesion mask as an output. In method evaluation, we performed an ablation study in which we assessed the impact of each of popcorn key features. Next, we compared the performance of popcorn with other state-of-the-art methods. Our results are backed with statistical analysis using Wilcoxon test. First, we studied the impact of consistency regularization, proximity graph, and pseudo-labeling. The results show that when removing one of popcorn key features, the segmentation accuracy drops compared to the full method, but is still higher than the baseline. This highlights the importance of each contribution in our pipeline. Second, popcorn is compared to other state-of-the-art strategies. We have chosen a method for each semi-supervised category: auxiliary task, pseudo-labeling, and consistency regularization methods. You can see the reference of the papers below. Even though all semi-supervised methods achieved higher dice than the baseline using label data only, we clearly see that Popcorn obtained the highest dice with a large margin. That's all, thank you for your attention. Feel free to contact us if you have any questions.